Thank you for coming to my talk, where on behalf of my co-authors, I'll be presenting LaserFactory, an electromechanical assembly and fabrication platform integrated with the laser cutter to make functional devices and robots, such as the quad rotor in this photograph. The way it achieves this is by combining geometry creation, trace making, and component assembly into a single unified fabrication system. By removing the need for human intervention in the fabrication process, LaserFactory democratizes the design and fabrication of objects embedded with electromechanical components. And researchers have previously explored combining fabrication techniques in a variety of ways. For example, LaserFactory and Fabricate used commercial machines to fabricate geometry in tandem with traces using a laser cutter and multi-material printer, respectively. And Peng et al. Combined a 3D printer with a separate coil winding mechanism to achieve higher conductivity wiring. Researchers outside SIGCHI have also combined geometry creation, trace making, and component assembly in various permutations, but not all together in a way that allows making fully functional devices without human intervention. Our goal, then, is to make fully functional devices in a single system by creating geometry, printing traces, and assembling components. To that end, we developed LaserFactory. The way we make functional devices is by using a hardware add-on clipped onto a laser cutter that prints traces using a silver extruder and can assemble components using a pick-and-place mechanism, while using the laser to cut material, forming the device's shape, and later again to cure the deposited silver traces. Let's walk through the fabrication pipeline. The first step in the fabrication process is to use the laser to cut out material, forming the device's geometry. Next, we use a silver extruder to deposit silver traces. Following that step, we use the pick-and-place assembly to collect electromechanical components and deposit them on the substrate. And finally, we use the laser in a defocus setting to cure the silver traces. And when the last trace is cured, the device is fully electrically connected, and in the case of a quad rotor, it can fly itself directly off the platform. And in the course of creating a system capable of this, we make 4 separate contributions: a hardware add-on, a motion-based signaling technique, a laser soldering technique, and a user interface. Let's start with the hardware add-on. The add-on itself is a 3D printed chassis fitted with commercial off-the-shelf components costing $150 worth in parts. Here you see the subsystems once more, shown as a CAD rendering on the left and a photo on the right. To set up fabrication, we mount the add-on to the laser head, and after placing a sheet of material in the platform bed and turning on the add-on, we can execute a job. Next, we'll describe how the add-on receives fabrication instructions via its onboard accelerometer. The add-on has no communication lines to the laser cutter, so how are fabrication instructions transmitted? This video illustrates extra movements during silver deposition as the extruder starts or terminates a new trace. These are instructions that have been encoded by appending specially calibrated lines to the beginning and ends of each trace when we create the fabrication file. These are then registered by an accelerometer on the add-on, causing it to deposit silver and assembling components at the right time. The effect is that the add-on has no communication with the laser cutter, ensuring that we don't rely on specific laser cutter firmware. Next, we show how to use the laser to cure the silver traces to make them conductive. To cure the silver, we defocus the laser to attenuate its power and match its spot size to the width of the silver traces. This lets us selectively cure only the traces without bulk heating of components or the material. Now I want to talk to you about the user interface that lets you design and visualize custom devices. We start with the design toolkit. Users start by selecting components from a part library, in this case, 4 rotors and a PCB, and deposit them on the canvas. Next, you can use wire tools to connect the components electrically by placing traces. And then they can place cut lines from the geometry tools, in this case, defining the perimeter of the quad rotor. Users can then inspect the fabrication file. And once the design is complete, users can launch the visualization toolkit. Users can use this to preview their 2D designs in 3D, as well as to simulate the full sequence of fabrication steps sequentially in order to inspect them for correctness. And we've used this process to create a variety of devices. In addition to robots, we also use LaserFactory to print general-purpose printed circuit boards, personalized devices such as a sensor-equipped wristband, and an H-bridge for bidirectional motor control. We also use LaserFactory to create 2.5D electronic devices, selectively heating up acrylic substrate until it becomes compliant and folds under its own gravity. We also use our assembly mechanism to cut and stack material to create 3D geometries. And with that, I'm very happy to take questions.